This is the solution of paper 1B of quiz 2. Question 1, it asks the mesh analyze. So before we do anything, we should put the numerical value next to the diagram. So E1 is 8 volt, V2 4 volt, R1 3K, R2 2K, and R3 1K. We have two loops. We can call this loop number 1, loop number 2. And to analyze the mesh current, we assume this is I1 and this is I2. So the next stage is we have to write down the KVL for each loop. So let's look at loop number 1 first. We first write down the KVL for loop 1. Now this is very important procedure. It has to be correct, otherwise it will mess up the rest of the question. Okay, the two loops you already given, we are going to analyze clockwise. But remember, it doesn't matter if I change or someone change the direction from clockwise to anti-clockwise. You just apply the same rule. Look at this case. If we first look at E1, the current enter E1 from this direction, and this is negative. So we have to put down 8 volt. But this time we have to use negative 8. So the first number is negative 8. Now you don't need to put down any unit because we know we are putting voltage, and the prefix is important but not the unit. Next, when the current enter R1, it enter here, and this is I1, and the R1 is 3K. So we write down the voltage straight. The voltage V is equal to IR, so you can write I1 3K, but we know the I1 will be our unknown. So when I write down here, instead of writing I1 3K, I will write 3K I1. So put the unknown after. And also we know this must be positive. So whenever the current passing through the R, it has to be positive. So this is positive here. Next is the current passing through R3. In here, R3 on your left hand side will be from top to bottom, and this is I1, but R3 share with another loop, the loop 2. In this case, the loop 2 here, the I2 going up on the right hand side. So this is I2. Now this is important point because we are analyzing I1. So you have to force the current consistently flowing from top to bottom. This is the direction of the I1. But I2 of the opposite side, which is opposite it. So we should write the current passing through R3 is I1 minus I2. Therefore, we keep the direction of the final current from top to bottom. Now, remember, we should write the voltage. So R3 is 1k, so we multiply 1k and we put positive here. So this is equation number 1. Okay, KVL for loop 2. We use the same argument. I2, the direction is clockwise. When it enter E2, it enter from the negative side. So we should put negative 4. Next, this time I2 for R3 is from the bottom to the top. So we have to maintain this direction. So in this case, we have to make I2 minus I1. So to make it consistent. So this is I2 minus I1. And the resistor is 1k, so I put the 1k here and positive. You may ask which one should be bigger. So this is mathematical trick. At this stage, we don't know yet. All you need to do is follow the rules set up by engineers. Solve the equation. Once you solve the equation, you will find the numerical value of I1 and I2, and then from here you can decide what is the direction and the magnitude of the actual current passing through R3. So at this stage we don't know. Now let's look at R2. R2, the current I2 passing through R2, there's only one current, so this is I2. So the voltage is 2k times I2. Remember, I always put the resistance first because I know I1 and I2, they are the unknown in this equation. So I put positive 2k I2 here. So this is our equation 2. So the next stage is you want to simplify these two equations. Now, these two equations, they are the key for our analysis, and they contain all the physics and the technique here. The rest is we want to solve this equation for I1 and I2 using whatever method you are familiar with. You can use elimination, substitution, or even using matrix method. So first, I will simplify equation 1. So I will put the minus 8 from the left side to the right hand side, and I focus on I1. So you will find this one will become 4k I1. For the I2 is minus k I2 equal to 8. This is equation 3. Now from equation 2, you do the same thing. You first put focus on I1. So the I1 here, and the coefficient is negative 1 because this is negative here, and this is 2k. So you nope, they're only negative 1, so you got minus k as the coefficient for I1. For the I2, you will have positive 3k I2, and you put the 4 from the left side to the right hand side. So you have a set of equation. It's much easier to manage. Next, we can use whatever method we like to use. So in this case, I use elimination. So I will say equation 3 add 4 times of equation 4. The aim is to eliminate I1. So if you do this operation, and this is plus here, and this I1, the coefficient will become 0. How about I2? So I2, you can say the coefficient is minus 1, positive 3, but 3 times 4 is 12. 12 minus 1 is 11. So you will get positive 11k I2, and here you will get 24. From here, I2 equal to 24 divided by 11k. And again, that's why we put the k here. Is very handy because 1 over k will become mini. So you will get 2.18 milliampere. Okay, once we find I2, we just substitute I2 back to the equation. Say we substitute I2 into equation 3. So 4k I1 minus k I2 is 2.18 mini. Again, no need for the unit, just the prefix, equal to 8. And this k here, this m here, they're like a sort of cancel out because 10 to the power 3 times 10 to the power minus 3 equal to 1. And if you do the calculation and rearrange this one, you will find I1 equal to 2.54 milliampere. Okay, next stage is you should calculate the current passing through R3. Now let's go back and highlight this one first. I2 is 2.18. I1 is 2.54. So I1 is bigger than I2. This is what we found. Let's look at this drawing again, the diagram. So we can say here this time we are pretty sure, and this is I2 is big, it's less than I1. So the current passing through R3 will be I1 minus I2, and the most important is it will be from top to bottom, because this is the direction of I1. Okay, so current I3 passing through R3 is equal to I1 minus I2, and this is 2.54 mA minus 2.18 mA, and you will get 0.36 milliampere. Now you should specify this from top to bottom in the circuit diagram. The voltage across R3 should be easy because it just Ohm's law. Okay, so 0.36 M, and R3 is 1K, so this is 1K, so you got 0.36 volt. So this is the example or how question 1 in paper 1B. Let's move on and look at the second part. In the paper 1B, the second part, you have a circuit diagram, and you can choose either using Thevenin or Norton equivalent circuit to find the current and the voltage across the load resistor RL. Let's first apply Thevenin equivalent circuit and see what you can find. Let's see question 2. We want to focus on the load resistor, and we want to replace the rest of the circuit with a potential divider. So what I mean is we have to replace anything outside with another new potential source, which we call the Thevenin voltage. And we found another resistance, which we call Thevenin resistance. Now, these two is everything outside the load. Now, we put the load back. This is our load. So from here, once we find this, we say these two circuits, from the point of view of the load, they are equivalent, because you can calculate the I passing through the load, and also you can calculate the voltage across the load. So from this point of view, if you just want the I here and the voltage here, these two circuits, they are equivalent. So what next stage is how to find the Thevenin voltage and the Thevenin resistance. First, I will show you how to find the Thevenin voltage. So I will redraw this circuit. In this redraw, I will first remove the RL, I mean the load. So keep everything here. This is 9 volt. And this one is 9k ohm. And this is 6k. And you have another one, this is 6k. And this is 2 opening. So what it means is you want to find if I remove the load and I measure the voltage across this A and B, what is the voltage? And we call this Thevenin voltage. Now, if you were in the tutorial, you remember I showed to you the voltage across AB is exactly the same as the voltage across CD. It means they are equivalent. So I can redraw this diagram again. And this one is here. And this is your 9k. And this is your 6k. So I first remove the 6k, and this point here is our C, and this is our D. So what we are saying is the voltage across AB, the Thevenin voltage, is exactly the same voltage here. And this voltage, if you see here, it is a potential divider. So this is very easy. And this voltage, the VCD, is proportional to 9 volt. The proportional constant, the denominator, is 9k plus 6k. The numerator, because we want the voltage across the 6k, so we put 6k here. And you should be able to see the value here is equal to 3.6 volt. Now this is exactly the Thevenin voltage. So we first find out the Thevenin voltage. Next stage, we find the Thevenin resistance. We have to find it separately. So there's a rule here. Again, we draw the circuit. So there's an additional thing you need to do is to kill all the sources in your circuit. The rule is, if you see the voltage source, you replace this one by straight line, it means a short circuit. If you see a current source, you just open it. Now here we have a voltage source, so we just short the circuit. So instead of E, we just connect this one here, and we still have our 9K, and we have 6K here, and we have 6K here. So what we are doing is we want to find, if we look at from these 2 points, this time A and B, if you measure the resistance, we ask what is the resistance across A and B, and we call this Thevenin resistance. Now if I redraw this circuit, in this case, now I want to draw your attention first. These 2 points, they are very important because they are the splitting point, they are the junction, and the C, D here. So now I withdraw this circuit like this. This is 6K, and you have split this one into 2 paths. One is another 6K, this one is 9K, and they withdrawn here. So this is our C, this is our D, so, and this is A, and this is B. So these 2 circuits here, they are actually equivalent. Now this is easy now. The resistance across AB is 6K in series of 9K and 6K. These 2, the last 2, they are in parallel. So we can write down this one like an engineer. We say that R Thevenin is equal to 6K in series, so it just plus 2 resistors, which is 9K and 6K, but this time they are in parallel, so we have to put a special sign here. If you plug this one and use the method, so 9K, you got 3.6, so this is 6K plus 3.6K. Therefore the Thevenin resistance is 9.6K ohm. Now we have everything here. We found out the Thevenin voltage, the Thevenin resistance. So let's go back to here. It means now the Thevenin voltage is 3.6. So this is 3.6 volt. The Thevenin resistance is 9.6 kilo ohm. 9.6 kilo ohm. So now we can calculate what is the voltage across RL. So it's easy because we can immediately recognize this is again the potential divider. So VL is proportional to, now this time it's not 9 volt, we are talking about this circuit. So the source, instead of 9, it becomes 3.6. So there must be 3.6 here. And the proportional constant denominator is the sum. So this is 9.6K plus RL. RL is 12K. So we just put the 12K here. And this is 12K. We want to get the voltage across RL. So this is 12K. We plug this one into your calculator, and you will find this is equal to 2.0 volts. How about the current? The current here, we can just use Ohm's law, V equal to, and this is 2.0 volt, and this is 12k ohm, and so you will get 0.167 milliampere. Next, we want to solve this problem with the Norton equivalent circuit method. So remember, they have the same circuit, but we are going to approach this problem with a different method. So the ultimate aim is the same. If we look at RL, we just want to find what is the current passing through RL, the load, and what is the potential difference across this one. So this is 2 points. Now, in the Thevenin method, we replace the west, the outside part, with a potential divider. In the Norton theory, or the Norton method, we replace the outside circuit with a current divider. So what I mean is, this time, instead of a potential source, we need to find a current source. Okay? And then we assume this current starts from the current source, and we assume this one split into two paths. The first, we go through so-called the Norton resistor, and the second one will be our load. So this will be RL. So this is how we imagine this case. So this time we replace the rest outside the load with this circuit, because once we successfully find it, we should know this current coming out from the current source. We call this Norton current. And when the Norton current passing through here, it will split into two paths. So the path 1, the second path. So all we need is find the current I passing through the RL, and then we use Ohm's law to find the voltage. And what we need to find, of course, is IN and RN. Let's do it now. First, we have to again redraw the circuit. Now, we do the same thing. We withdraw this one. This is 9 volts. We connect this one. This is 9K. And this is 6K. And 6K here. Now, there's a one thing different. In Thevenin, we just remove the load resistor, and then we say what is the voltage across it. Just recall, this is what we do. We remove the load and ask what it is. But this time we need the current. So yes, we will remove the load, but at the same time, we must reconnect this one, give a path, and we want to find what is the current passing through this point, and we call this IN. To do this one, we now analyze this circuit here. If we know this is R1, of course, if I put this one back, R1, and this is R2, R3. If we know the current passing through here, this is I1. Can you see this point here is split into I2 and I3. So the Norton current is the current passing through this one. It's the same. So how to find it? We should first find I1, and then we can use the current divider. What I mean is I3 or IN. The IN is equal to I3. They're the same. This, if you look at this circuit here, it is a current divider. So this is proportional to the overall current, I1. So this is I1, and the proportional constant is 6K and 6K. Now this is easier because they are the same. But remember, if they are not the same, if they are not equal to 6K, we must use the value of this one, which is the one control the current. So this is 6K in this case. Now the question is how to find I1. Now to find I1, how about I redraw this circuit? This is 9 volt, and if I withdraw, put a 9K here, this is where you split, and this is 6K, and this 6K, and this is the return. Okay, so if we look at identify the point which they split, this is always important. This is A, this is B. So this is A, this is B. So we are saying is, can we find this, the overall equivalent resistance? And the answer is yes, because this equivalent resistance R is 9K plus 6K parallel to 6K. So this is 9K plus 3K, and this is 12K. So in this circuit, you got 12K here. So this is 12K ohm, and now you know the source is 9 volt, so you can see what is the current, the total current. And of course the total current is 9 over 12K, the same 9 over 12, and you got 0.75, 1 over K become milli ampere. So this current here is 0.75 milli ampere. Now this current is the current coming out from the 9 volt potential source. So this current must also equal to this current, because this is the current. So this is 0.75 milliamp. It means this current is our I1. Now we found the I1. Going back to here, this is what we need. So we know this is, incidentally, this should be half of I1, which is 0.75 milliamp, and you should get 0.375 milliamp. This is our important, this is our IN. Okay, so we found the IN here. Our current source, it will produce a current which is 0.375 milliamp. Next, we want to find what is the Norton resistance. Now, this actually is easy because it is exactly the same as the Thevenin resistance. We repeat here. This time, we do the same thing. We kill the sources by, if you have a potential source, you short circuit. If you have a current source, we replace it by open circuit. So we have a potential source. So now you short the circuit. This become here, and this is 9K, this is 6K, and this is 6K. Now you remove the RL, the load. This is the key point, and you want to find what is the resistance when you measure across A and B. So again, if we draw this circuit here, this is what you should see. This is your A, this is your B, and this is C and D, and this is C and this is D. And this one is 6K, 9K, 6K. Or the Norton resistance, beg your pardon, is 6K plus 6K parallel 9K. So again, you will see this is 6K plus 3.6K. So you get 9.6K ohm. So I just put it back here. This is 9.6K. Now, once we got this one here, the rest is very easy, because now we can look at this circuit here again. We found the Norton current, which is 0.375. We found the Norton resistance. This is the same as Thevenin resistance. It's 9.6 kilo ohm. Now, we replace this one. We use this one to replace anything outside this circuit except the RL. So we put the RL back. And now we say, what is the current passing through the load, the IL? You can recognize immediately this is a current divider. So IL proportional to IN, and the proportional constant is Rn plus RL. Now remember, it is the opposite branch. We are talking about the current passing through RL, but it is the Rn, the opposite resistor of the other branch, control the current. So it means the numerator must be Rn. Now you put everything back. Rn is 9.6K. This is 9.6K. And the RL is 12K. And we just found out this is 0.375 milliamp. Plug this one into your calculator. You will find this is 0.167 milliamp. And the voltage, of course, you can use Ohm's law. This is 0.167 milli. R is 12K. And you will find the answer is 2.0 volt. And can you see this is exactly this number, exactly the same as these two numbers. It means from the point of view of RL, you can replace the outside circuit either by potential divider. This is what the Thevenin theory say, or a current divider. This is what a Norton theory do. So both methods correct. And the most important thing I hope you will appreciate is that you really need to draw each state, draw the diagram. And you have to know the method. Say, you should know the equation, how to find potential divider, current divider, Ohm's law. You should remember when you do the Thevenin, you just remove the load and find the voltage across it. When you do Norton, you remove the load, but at the same time, you reconnect it, so you can find the current passing through it. The Thevenin resistance is the same as Norton resistance. All you need to do is you kill the source and then remove the RL, and you find the overall resistance in this new network. Now this is the procedure, and this is important to know the procedure. Also, you should know how to kill the source. When you find the Norton resistance, you need to kill the source. You have to replace the voltage source by the short circuit, current source by open circuit. That is all you need.